Hello, welcome. Yeah, so first and foremost, as always, thank you, Lord Christ. You're amazing. I love you. And yeah, so in this video, we're going to do harder practice on partial derivatives. Now, on the title, I say advanced examples. I first had harder examples because we saw the basics of partial derivatives. We saw some, typical examples, and we actually started by learning why partial derivatives make sense, and we looked at why the definition of the partial derivative makes sense, and we had some visuals going, so check out those videos. But yeah, so after the initial discussions on partial derivatives, we came across what's called Clairaut's theorem, aka Young's theorem for mixed partials, and there were two videos on that. First, just introducing it, and then extending it, right? And so I'll remind you what the extension of Clairaut's theorem said for mixed partials. And again, Clairaut's theorem sometimes is called Young's theorem. So I'll say both. But yeah, what we've got here is an application of Clairaut's theorem, aka Young's theorem. And we will see in these examples the power of that theorem on mixed partials, Clairaut's theorem. Now, the questions are kind of long. I mean, the video isn't long. We're going to make the questions simple. So the whole point is that these would be hard partial derivatives to figure out, but by using Clairaut's theorem, we're going to make them super simple. But I, couldn't write them all at the board, so I have them here. I don't know what you're able to see. Definitely not my face, I know that much. But here, there's nothing. I'm just showing you that all I've got on this paper is the questions. Yeah? Okay, cool. Really quickly, let's recall what Clairaut's theorem, or the extension of it, said for mixed partials. So it essentially said that, like, if you have, like, fx, say, yx, so that's three partial derivatives in a row. First with respect to x, and then you take that result and do the partial with respect to y, and then you take that result at that point and take the partial with respect to x to conclude. And what we said is this, for example, is equal to fxxy, right? And in turn equal to fyxx, right? Okay. And the criteria for this equality to hold is that all three of these mixed partials are continuous in some domain D containing the point AB at which we're evaluating them, right? So like basically, even though I'm abbreviating, this is a function of two variables, let's say. So it's the partial with respect to x, then y, then x of f of xy, right? And so the input would be AB, and any xy in this disk is allowed. So we're saying like this disk is the domain of this function, right? After the three mixed partials. And so if after three mixed partials, this is continuous in here, right? For any AB I take in this domain, and this too is continuous, and this too is continuous in the same domain, then the equality holds, yeah? Okay, so we're saying equality does not hold if continuity is not true about these mixed partials. But, it didn't matter how many times we take partial derivatives. In other words, I could throw like a y here, and a y here, and a y here. Now, there are other varieties of two partials with respect to x and then two partials with respect to y that we can write than these three. But basically, I can keep doing this, and so long as continuity in the disk holds, then the equality also holds. So we're going to exploit this like to fantastic effect in the examples that I'm going to provide you here. I hope you enjoy them and think that this is a very useful theorem to the extent that I think it is. Okay, all right. So first question is this. Oh, by the way, if someone gives you a cough drop and you're not sick, don't take it. Okay, just random thoughts. Okay, all right, a little bit sick because, well, I just didn't listen to the advice I gave you when my head was telling me, listen. Okay, so this is equal to, and then it's x plus, xy cubed over the natural log of sine of y. Jesus Christ. Okay, this is fancy curve, e to the minus y squared. Okay. That division sign needs to be extended. Okay. Now I'm like tampering too much, right? Okay, so this is the function. I don't like this line. Let me redo that, please. Okay, that's better. All right, I'll live with that. Okay, so this is our first curve, and what we need to find is fx, yx. No, it's just fx, yx. So this is what we need to do. And again, we want to exploit Clairaut's theorem, because for example, we know instead of doing this, we could do fxxy, right, and so on. So how do we want to start? Do we want to do two partials in a row with respect to x and then a y, or do it exactly as it's written? What's beneficial? Well, let's see. So if you look in the numerator, notice that we can factor out an x. And so factoring out an x in the numerator would mean that we've got like x times, and then what is it, 1 plus y cubed, like that, right? This x seems too tiny. So let me write the x right here. Okay, so we see that this here, when we're considering partials with respect to x, this here is a constant, because it says the natural log of sine of y. So this is a constant. This too is a constant. I see. And so basically, like, this whole thing might as well be like 2x, right? A constant times x, where like basically the only thing that's not a constant when we're considering the derivative with respect to x is the x that we had here, and I can write it on the side. I can make it more clear that now the 2 is equivalent to this quotient, right? So what we should do is take the partial with respect to x to start, right? So if we do that, we're gonna get, so I'm gonna say, like, let's start with this, fx. Fine, if we do this, fx of xy, and again, I just write fx, and yes, it's f sub x, but don't say f sub x. In context, if you say fx, we all know what you mean. Okay, so, but it also, we know that it's a function of x and y, so we don't need to write that. So fx, what is that equal to? Again, this is like 2 times x, so it would be 2, which is this, right? So we'd have 1 plus y cubed over the natural log of sine y, and then plus e to the minus y squared. Right now we're at fx, and where we need to get to is fx, yx. Now, if we do fxy next, well, we're doing the partial with respect to y of this, and that would require a quotient rule. I don't want to do that. Why would I want to do that? So I'm going to do this, fxx, and then I could write fxxy, and I know this is the same as that. Okay, so I'm going to, once again, take the partial with respect to x of this. But wait, everything here has y in it, or it's all basically one giant constant, as we already said. So when we do fxx, well, we're doing the derivative of a constant with respect to x, and so the constant is going to be 0, so this is equal to 0. All right, cool. So then fxxy is the partial with respect to 0 of, sorry, the partial with respect to y of 0. The partial with respect to y of 0, right? That's 0. Got it. So then we conclude that this must equal 0, this here, since it's equal to this here. Yeah, okay, you see what would have otherwise been a very hard partial derivative, well, I don't know, very hard, but kind of challenging partial derivative question is now made very simple, right? Okay, cool. So let's keep moving and on to the next one. All right, on to the next one. And what's the next one? This is cool, so you'll appreciate this. This one is, you have f of x comma y is equal to, it's equal to x to the power y divided by the natural log of x cubed, right? And what we need to do is a lot. We need to do f y x y x y. Okay, whoa, madness. All right, it's okay. All right, first thing first. Well, yeah. So if we do the partial with respect to y of this, right? Notice that the denominator is a constant. If we're doing the partial with respect to y, because the denominator is the natural log of x cubed. So this is all about x, so this is a constant. And so in the numerator, since we're considering the partial with respect to y to start, in the numerator we have a constant to the variable power. And so let's remind ourselves what the derivative of that is. Sorry. So if I have like and the good old, like, you know, calc 1, if I have y equals a to the t, what would the derivative of that be? Well, we know that it's going to be y prime, which is the natural log of a times a to the t. Okay, I have a video explaining why the derivative of a constant to a variable power has to end up being this. Yeah? Now, I can easily convince you that, like, if y is specifically e to the t, that is when the constant a is e, then we know that y prime is going to, well, if this is true, it's going to equal the natural log of e times e to the t, and natural log of e is 1, so y prime is going to be e to the t, so you should understand that this is actually good. Yeah, this little formula for derivatives like that works. Now, why am I discussing this at length? Because, again, we're going to consider taking the partial with respect to y to start, meaning the denominator is a constant, and in the numerator we have a constant to a variable power, where the variable is y, right? So we see that the derivative of the numerator is going to be the natural log of x times x to the y power. Again, by using what I did over here, right? And of course, the denominator is a constant, so we just keep it, which is the natural log of x cubed. Yes, now I can simplify, but I'm not going to. And by the way, you should follow that this is fy, right now. Okay, good. Okay, so then should we follow this with the derivative with respect to x, the partial derivative that is with respect to x of this, so we get fyx? I think not, because, well, there are a lot of x's, and so if we follow this with the partial with respect to x, well, we'll have to apply quotient rule, and I don't want to do that. Even if we simplify here, we still have to simplify natural log of x over natural log of x cubed. We still have to do quotient rule, and what remains if we next write fyx. So what I'm going to do instead is I'm going to go fyy. Okay, well, fyy, notice, well, again, this whole thing is a constant, and so the derivative of this, x to the y, just as before, is going to be the natural log of x times x to the y. So we write the natural log of x, this is that, times, now the derivative of this is the natural log of x, oh wait, I could just write natural log squared, okay, and then times otherwise x to the y, right, and then over natural log of x cubed. Got it. Now, it should be pretty easy to see that we should next do fyy. Right? fyyyy. So let's do fyyyy. So fyyyy, because remember there are 3 y's, and what we have to find, well, okay, again, this here is a constant. The derivative of x to the y is going to be the natural log of x times x to the y. So we're going to have natural log of x squared times natural log of x, so that's natural log of x cubed, otherwise times x to the y, right? And then all of this over the natural log of x cubed. Ah, how convenient. Now we should cancel these, right? We do. Okay, so we see that fyy is going to be x to the y. So fyy is simply equal to x to the y. All right, got it. So then, obviously, now we have no choice. We have to follow this with fyyyx. And when we do, well, fyyyx, this time we're seeing y is the constant and x is the variable, and so we just use the power rule. So that's y times x to the y minus 1. Got it. And once more, adding partial with respect to x of this, we get to what we want. fyyyxx is going to equal y times y minus 1 times x to the y minus 2. Yeah? Okay, cool. Yeah? I'm not done though. I gotta keep going. Okay, alright, so let's do that. Alright, so obviously what I wrote now with 3 y's and 2 x's is the same as that, so I'm saying we're done with this problem. Okay, so how many more will go? Like, well, 2 more, so it's not so bad. Alright. I mean, it was never bad, it's fun, right? But yeah, I'm always trying to carefully choose my examples so that you guys get a lot out of each different one. Okay. fxy equals this the square root of and it's 1 minus e to the x, and then over x squared, and then plus y cubed. And what we need to do is find fxy. So find fxy. Okay, cool. So we know if we do the partial with respect to x to start, we have to do quotient rule here. And not only do we have to do quotient rule, the numerator involves a square root. So we know that that kind of like, it's not hard, but it's more work than we want to do. So let's start with the partial with respect to y that way. When we write fy, we see that this here is just a constant, so its derivative is 0. So we're just going to get 3y squared. How nice. Okay, and now we do fyx, right? fyx, and so we follow this result with the partial with respect to x of it, and so that's going to be 0. And actually, it wasn't very hard to see that we're going to get to 0, even if we went in this direction, because, well, all right, let's just talk high level. So if we did fx, right, fx, well, that's a partial with respect to x of this. Fine. As I said, you have to do quotient rule here, but when you're doing it with respect to x, this is a constant, so this goes away. But then you have to follow fx with y. After doing quotient rule on this, all you're going to get is a bunch of stuff that has x's in it. So when you follow it with fxy, then you're going to get 0. That should be easy enough to see, yeah? Okay, cool. All right, so uno mas, and then we are done, at least for this video. Otherwise, you're going to get videos till you get sick of hearing me. It's like I get sick of hearing me. Well, actually, that happened a long time ago. I'm kidding. All right. So, I guess save the best for last. And in this one, this is what we're doing. It's a function of 3 variables, fx, yz equals, so the long expression, sine of, and then it's xz, and then plus 1, right? And then plus 1 over square root of x squared plus y, and then plus arctan yz over y plus z. Got it. Okay. Now, y'all, what do we have to find? We have to find fx, y, z. So this is what we have to find. We have to find fx, y, z. Obviously, we know that we could do it in any order. We could do f, y, x, z, or f, z, x, y, or yada, yada, right? Okay. So basically, the question is, which do we start with? The partial with respect to x, or partial with respect to y, or partial with respect to z? Each, turns out, has an advantage. If we do the partial with respect to y, then notice that this here is a constant. So as soon as we write fy, we see this is going to turn to 0. But this here has a y in there, so this is not a constant, and we know we have work to do here. And likewise, that's if we start with fy. Okay, if we start with fz, then this has a z, so it's not a constant. This is a constant, so it'll turn to 0. And this has a z, so it won't turn to 0. And if we start with fx, this is not a constant, this is not a constant, but this is. Okay, so each has an advantage. And I don't know why, but maybe out of instinct, want this gone. So I'm saying I'm going to start with fy. And I already wrote it down anyway. So if we start with fy, as we said, this is going to turn to 0. Because there's no y in this, so this whole thing is a constant. And this I could rewrite as x squared, not like that, better, x squared, I like this parenthesis a lot better, plus y to the negative 1/2, right? That's what we had. Okay, so, because, well, we need to take the derivative of it, and it's friendlier to take the derivative of when it looks like this. So we're going to write negative 1/2, and then x squared plus y to the negative 3/2 and then times what? Times 1. Why you say times 1? Because we're doing fy, so anything with x is a constant, so this x squared is a constant, so its derivative, when we do chain rule for the derivative of the inside, the derivative of this is going to turn to 0, plus the derivative of that is just 1. So I don't need to write times 1, I'll just keep it like this. Plus, we know the arctan derivative, so I'll cross over here. The arctan derivative is 1 over 1 plus whatever is in it squared, right? So whatever the argument is squared, so the argument here is yz over y plus z, so all of this squared, and then times, by chain rule, we need to multiply by the derivative of this inside, and we're doing fy, so yeah, we need to do chain rule there. Actually, I backtrack. This is harder than like it would have to be if I did, like, for example, fx to start. I want this gone. So, sorry guys. Well, actually, it's a lesson still. It's a useful lesson. When to quit. No. Okay. All right. So, let's do fx to start, right? If we do fx, well, yeah. So here, we have to do cosine of xz and then plus 1, and then by chain rule times the derivative of the inside. The derivative of this, well, this is like a constant times x, and this is just a constant, so the derivative of this is 0, but the derivative of this is z. So I'm going to have z times, this equals z times, and then cosine of xz plus 1. And then what about when we get to here? Well, because of the x there, we do have to do derivative in this part, and that's going to be minus 1/2, and then x squared plus y to the negative 3/2 times 2x. Right? Okay, cool. And then this is why we're so happy with this root. Right? Plus 0. 0. Good. Alright. So that's why we liked that. Okay, and now what should we do? Y or z? I want to do partial with respect to y next. So we have I'm saying let's write fx y. I don't know if you disagree, but I agree with me. Like, this is why I can justify it. So when we do the partial with respect to y next, this whole thing is a constant. Otherwise, we'd have to do a product rule if I said fxz in this part, and I don't want to do that, right? Okay, so, but then, even though we have to do product rule here for fxz, like, if we next did z, this whole thing would turn to 0, right? And I actually think this is uglier than this. So, backtracking once again, I'm going to go fxz. That way, I do product rule here. So, product rule is, well, the product is between z and cosine of xz plus 1. So, we do 1 times and then cosine of xz plus 1. And then plus z times, the derivative of cosine is negative sine, so this is actually minus, and then sine of xz plus 1, and then by chain rule we multiply by the derivative of xz plus 1. We've been through that. That's z, so I'll just write a square right there, yeah? Okay, but then the derivative of this, since it don't got no z, is minus 0. Well, the minus for that, but great. Okay, now finalement we do fx zy. Got it. Do you see a y here? I see no y. Do you see a y? I see no y. And therefore, I don't like that 0. 0. 0, 0, 0. Alright, I hope you enjoyed this. Keep watching. Take care.